Well, atoms are way too small to count, right? So we can actually use mass to count them. We can count atoms by weighing them. We need to know the number of atoms because chemical processes happen between individual particles. They happen on the particulate level. And so when we're looking at chemical reactions, we need to be looking at numbers of particles, not at the masses. But we can't count them. If we know how much they weigh, we can count them by weighing them. It's a little bit like, going to the hardware store and you need some nails, and old-fashioned hardware store, and you've figured out you need 2,000 nails to build your fence. You're not going to stand there and count out 2,000 nails, are you? You could, but it would be really tedious. The old-fashioned hardware stores, they've got this big metal scoop and they've got a scale. And there's a little sign there that says, 300 nails per pound or whatever. And so you do a little unit conversion and you figure out how many pounds of nails you need. And do you have the exact right number? Probably not. Is it close enough? Yeah. And it's way easier than counting out 2,000 nails. So that's how we count atoms. So, the mole. I keep forgetting every lecture that the little furry critter stuck on the pole just makes me crazy while I'm lecturing. I want to say that's a mole, but it doesn't really look like a mole. Oh, is it Seth Yates's little pet? His pet lemur? Oh, well, that's good to know. Thank you. I think I'm going to have to, I might even do it this afternoon, go on Amazon.com and buy a little stuffed mole and have it chasing the lemur. Because the mole's important. A mole is a little furry animal with poor eyesight that likes to dig in the dirt, right? What's another meaning for this word? Pronounced a little different. Mole. Sauce, right? Good Mexican food with mole. Guacamole is my favorite, right? Avocado sauce, I suppose, if you translated it. But that's neither of those terms are what we're using. They also refer to a mole as a spy. A spy could be referred to as a mole. But in chemistry, a mole is a unit. And that's kind of a stretch. Hopefully all of you guys, because you have a prerequisite coming in here, hopefully everybody's heard of the mole before. But maybe it didn't make all that much sense before. So that's why I'm kind of going into this. The mole is really important. So let's stop talking about that for a minute and look at regular things. A dozen things is how many things? It's 12. A dozen donuts is 12 donuts. A dozen cars is 12 cars. A dozen countries is 12 countries. Doesn't matter what it is. Dozen is a particular number. It's the number 12. And we're all okay with that. There are other counting units like this that you may or may not have heard of. Do you know what a gross is? It's disgusting, right? No, a gross is a dozen. So a gross of something is 144. Ream is another counting unit used for sheets of paper. How many pieces of paper in a ream? 500. Why? Because they decided that would be a good number, and everybody just follows along. So the chemists have a unit like this as well. I call it the chemist's dozen. Just the number's different. We use it the same way as we would dozen. So it's the mole. It has an abbreviation, MOL. I don't know why you need an abbreviation for such a small word, but there it is. There's no abbreviation for molecule. I'll harp on that a lot. What is this number? It's 6.02214 times 10 to the 23rd particles. That's a 6 with 23 zeros after it. That is a really big number. I mean, you just can't come close to getting your mind around how big of a number it is. A mole is an amount of material, an amount of an element, amount of a compound containing this many particles. Okay? So as an equivalent statement, we can say 1 mole equals 6.02214 times 10 to the 23rd particles. Now, we don't usually need that many significant figures, so generally we're just going to use 6.022. For most of our calculations, that's going to be just fine. And they do know this number to more decimal places as well, if you ever need that. It's called Avogadro's number, in honor of the man whose work led to the discovery of this number. So any questions yet? Just like a dozen means 12, mole means 6.022 times 10 to the 23rd. So it's that number of anything. You could have a mole of marbles, 6.022 times 10 to the 23rd marbles. That would cover the surface of the Earth to the depth of about a mile. That's a lot of marbles. A mole of sand grains, 6.022 times 10 to the 23rd sand grains. I think that would be about the size of Mount McKinley, sand grains. That's a lot. So 1 mole of anything, 6.022 times 10 to the 23rd. Now I have to tell you a story. So chemists, well, backtrack. You've heard of Pi Day? The mathematicians have Pi Day. It's March 14th, because pi is 3.14159, blah, blah, blah. So they celebrate Pi Day. And Star Wars people like May the 4th. May the 4th be with you. No? No, okay. Chemists celebrate Mole Day. Mole Day is October 23rd. Technically from 6:02 a.m. to 6:02 p.m. But that's Mole Day. So my husband's a chemist. I'm a chemist. Our 4th child was born on Mole Day. So he's our little mole baby. And what's even better is he weighed 10 pounds, and he was 23 and a half inches long. So he was 1023 on 1023. The only thing that would have been more perfect would be if he had been born at 6:02 a.m. or p.m. Did my best. It was 8:30. You can't have everything. But so we call him our mole baby, and we actually had a very brief but out loud discussion. Should we give him the middle name Avogadro? And we said no. So I think in retrospect that was probably a wise decision. But anyway, that's my mole story. So the second thing we need to understand about the mole is, where does this crazy number come from? We just didn't pull it out of the air. It actually has a reason behind it. So pure carbon-12. One isotope of carbon. Mass number 12 means 6 protons, 6 neutrons. They all have the same mass. So what they decided was, if we have exactly, as best we can, exactly 12 grams of carbon-12, that the mole is equal to the number of atoms in 12 grams of carbon-12. So 12 grams of carbon-12 is equal to 1 mole of carbon atoms. What that means then, well, I'm getting ahead of myself. Never mind. It'll come. We'll get to it. So there's a relationship between moles and numbers of atoms or molecules, and we need to become comfortable with converting. So here comes dimensional analysis back at you again. This is the same as converting between eggs and dozens. So if you get confused, do the calculation with the word dozen instead of mole, set everything up, and then just switch the units and the numbers. So here, 1 mole is equal to 6.022 times 10 to the 23rd atoms. We can have this conversion factor or that one, whichever one we need. So let's do an example. A pure silver ring contains 2.8 times 10 to the 22 silver atoms. How many moles of silver atoms does this contain? Well, we're starting out with silver atoms. 2.80 times 10 to the 22 atoms. And we are trying to convert to what unit? Moles. We know a relationship between atoms and moles, and so we can go directly from atoms to moles. So that many atoms, we're going to have one conversion factor. We put the units in, and the units tell us where to put the numbers. We want mole on the top and atoms on the bottom because we want the atoms to cancel out. Then we have to get Avogadro's number in there. Is it Avogadro's number of moles is equal to 1 atom, or is it 1 mole equals Avogadro's number of atoms? It's the second one. So here's where, if you're a little wobbly, think dozen and eggs. Dozen and eggs, where does the 12 go? Oh, well, we know that. It's 12 eggs in a dozen. The other, 1 egg is a dozen. I'm sorry, 1 egg is 12 dozen. That doesn't make any sense, does it? So you can always revert to eggs and dozens if you get mixed up here. Because that's probably the most common mistake that people make, is they just put the number in the wrong place. Now we've got all of our numbers in place. Here is where you have to use scientific notation on your calculator. I have yet to see a calculator that will allow you to enter Avogadro's number in decimal form. No calculator has 24 places on it. So this is where you need to become very familiar with your EE, or some calculators it's EXP button. So remember that that button stands for times 10 to the. I know some of you've got this down pat, you're good. Others, this has just been this thorn. But I wrote it out right and the answer came out wrong. So do this with me. I'm going to call out the buttons I'm pushing. 2 point, that's the decimal point, 8, 0, EE. When I press the EE button, I think times 10 to the. You're not going to press times. You're not going to press 10 to the x or anything like that. Just the EE button, and then 2. And then we're going to divide by Avogadro's number, which is 6.022 EE 23. And we press the equal sign. We write it over here, and I get 0.046496181, and the unit would be mole. Did you get that number on your calculator? We're going to be doing a worksheet in lab this morning. It'll still be this morning. And if you're having issues with your calculator, I'll help you. It's always your calculator's fault, and so we just have to train it to work correctly. How many significant figures should we round that off to? 3. Our starting number had 3 significant figures. Avogadro's number, as we used it, has 4. So you don't want Avogadro's number to be limiting the number of significant figures in your answer, but most of the time in lecture problems that won't happen. So 0.0465 moles. Any questions? Yes?
Mine did this instead.
Okay. So that was converting between number of particles and mass. I'm sorry, that wasn't mass, moles. That's good, but that's not the really useful thing. What we really want to be able to do is convert between mass and amount, number of moles. To count them by weighing, we need the mass of 1 mole of atoms. This is called the molar mass. The molar mass, because it's the mass of a mole. So an element's molar mass in grams per mole is numerically equal to the element's atomic mass in atomic mass units. So what is the atomic mass of sodium? as 22.99. Yeah, depends on which periodic table you look at. So 22.99, that's the atomic mass. Atomic mass unit, that's the mass of one atom. Right? We just talked about that. If we take that same number, the atomic mass, and express it in grams, that's the mass of 1 mole of those atoms. So the number under the element symbol does double duty. Tells us the mass of a single atom in atomic mass units, tells us the mass of the chemist's dozen in grams. And the reason that works is because of how the mole was defined. So if we find aluminum on the periodic table, the number underneath it is 26.98. That means that 26.98 grams of aluminum is 1 mole of aluminum. 1 mole of aluminum is Avogadro's number of aluminum atoms. These are great conversion factors. 12.01 grams of carbon equals 1 mole of carbon. 1 mole is Avogadro's number of carbon atoms. Helium, 4.003 grams equals 1 mole. The masses of 1 mole are different because the particles have different masses. Lighter the atom, the less mass in 1 mole. So the molar mass of an element allows us to convert between the mass in grams and the amount in moles of that element. So for carbon, we know that 12.01 grams is equal to 1 mole of carbon. So we have both of these conversion factors. We can use whichever one we need. So let's do an example. Calculate the amount of copper in moles in a 35.8 gram pure copper sheet. So we've got 35.8 grams of copper, and they want us to calculate what? Moles. Moles of copper. So I'm trying to demonstrate dimensional analysis as we go along. So if you've got it and you find it tedious, just be patient. This is what they're giving us, the number of grams of pure copper, and they're asking us how many moles. Calculate the amount of copper in moles. Well, there's a direct relationship between grams and moles of an element, and it's on the periodic table. So we can do this in one step. 35.8 grams of copper. We're going to have one conversion factor. We're going from grams to moles. So we're going to put moles up here. We're going to put grams down here. So the grams cancel out. Dimensional analysis. To find the numbers, we look at the periodic table. So for copper, 63.55. 1 mole is 63.55 grams of copper. It's always the mass of 1 mole. And then we just use our calculators. 35.8 divided by 63.55. As so often happens, we get a big old mess. Blah, blah, blah. The unit there is mole. It's always a good idea to write down more digits than you think you need. You don't necessarily have to write down all of them, but write a bunch of them down. Because if you make a mistake in your rounding and you have too many digits, you don't have to do the calculation over again. If you chop off too many and don't write down the rest ever, then if you find out you didn't have enough significant figures, you have to get your calculator out and do it over again. So I think it's always a good idea. Write down the whole thing and then look at sig figs. How many significant figures in this number? 3. And how about this conversion factor? I'm hearing 4 and I'm hearing infinite. Well, let's think about it. 1 mole we can assume that that is exact, because we're comparing grams to moles. Here is where the question is. How do we get this number to 63.55? Well, from the periodic table. How did they get it to put it on the periodic table? Use mass spectrometry to separate the different isotopes and find the abundances and do the calculation. That's one way. Is that an exact process? No. Molar masses are not exact numbers. So as I've written it here, this has 4 significant figures. Now, the periodic table on the wall here actually says 63.546. That has 5 significant figures. Never round off to less than 4 significant figures. But if you want to use 4 sig figs, I'm fine with that. You'll see that most of the examples we do, the number that you're given has 3 significant figures. So using 4 significant figures in your atomic mass is not going to affect your answer. What I don't want you to do is I don't want you to round atomic masses to whole numbers. Don't call this 64. That's going to introduce a lot of error. Okay? The best thing is just use all the digits that whatever periodic table you're looking at gives you. So as I've done it, this has 3, this has 4, so we should keep 3 and report our answer as 0.563 moles. Any questions? Yes?
What about oxygen? Can you run that for
Oxygen, 15.9994. If you round that to 4 significant figures, it does come out to be 16.00. You should still write it as 16.00. Good question. Anybody else? If you're doing a rough and dirty calculation, just to see if your answer's ballpark, like we talked about those order of magnitude estimations, then it's okay to do that. But if you're calculating your percent yield for your experiment or something, don't use ballpark numbers. You want to use the best numbers you can. So now we have everything we need to count atoms by weighing them. So you would obtain the mass of your sample. You'd convert the mass to the amount in moles, and then you'd convert to the number of atoms using Avogadro's number. So your book is showing you to do this in 2 steps: grams to moles, and then to number of atoms. That is fine. You can also actually do it in 1 step. So I'll show you both ways, and then just use the one that makes the most sense to you. How many carbon atoms are there in a 1.3 carat diamond? Diamonds are a pure form of carbon, and 1 carat is equal to 0.20 grams. Well, this one is not as straightforward as the last one we did. So let's pull some of these numbers out. We've got 1.3 carats. And then we've got this relationship. I'm not going to rewrite that. This is written out so nicely right there. What are we trying to find? How many carbon atoms? So this is what I'm going to start with. This is a relationship between 2 units. I'm going to need that as a conversion factor. But what I'm trying to find is number of carbon atoms. So here we've got carats to grams. So we could go from carat to grams. And then we have 2 options. The previous slide showed that you can take mass and go to moles and then go to atoms. And that works. It's fine. You can also go directly from grams to atoms. So I'm going to show you both ways. 1.3 carats. I can never remember the abbreviation for carats, so I'm going to write it out. And this top one, we've got 1, 2, 3 conversion factors. So I'm going to put out the 3 lines. Carats to grams to moles to atoms. Carats to grams to moles to atoms. And then I'm going to take this unit and bring it into the denominator, because I want those to cancel out. I'm going to put grams down here, and I'm going to put moles down here. Units. We're just canceling out units. The hard part is getting the plan, the path. Once you've got this, you just follow the pattern into this. Relationship between carats and grams. That's given right here. Keep the numbers with their units. So 1 carat, 0.20 grams. How about the relationship between moles and grams? 12.01, periodic table. 1 mole of carbon. I'm going to use the full one this time. Why? I don't know, because 12.011 is what the wall periodic table says. How many atoms, how many moles? 1 mole, Avogadro's number of atoms. So we've got 1 mole here, and this big old number is often hard to fit in. 10 to the 23rd. So, calculator time. 1.3 times 0.2 divided by 12.011 times 6.022 EE23 equals, calculator says 1.604395, and that's plenty, times 10 to the 22, and the unit is atoms. Then we have to look at sig figs. How many sig figs should that have? 2. 1.3 carats. That's a measurement, 2 significant figures. This relationship, 1 carat is 0.20 grams. That's a leading 0, doesn't count, but the 2 and the 0 count. This has 5, as I wrote it. Avogadro's number has 4. This limits us to 2 significant figures, so I'm getting 1.6 times 10 to the 22 atoms. Yes?
1.3 times 10 to the 22nd. Yeah, I got 1.3.
Okay, you guys get 1.3. So this is why you do it twice. Because apparently, my calculator shows on the display what I typed in. I typed in 1.6 instead of 1.3. So I had a brain fart, basically. That's what my husband calls them. So do it again. It's always a good idea to do it twice. I usually don't do it twice in class because I count on you guys doing it like you just did and saying, hey, wait a minute, that's not right. $1.303571, blah, blah, blah. Does that look better? We're going to round that to 1.3 times 10 to the 22 atoms. Is it a reasonable number? It's really, really big, isn't it? But a 1.3 carat diamond, that's a pretty good sized diamond. That's something that you can see and hold and handle, right? And so it must have a ginormous number of atoms in it. If you came up with 1.3 times 10 to the minus 22 atoms, would that be a reasonable number? No, because that's less than 1 atom. You can't have less than 1 atom. 1 atom is the smallest piece of carbon. So how would we do this with one less step? Okay, so 1.3 carats times 0.2 grams per carat. That part's the same. But now we're going to go from grams directly to atoms. So we're going to put grams down here and atoms up there. This is poor planning on my part. Well, what's the relationship between grams of carbon and atoms of carbon? Well, 1 mole of carbon equals 6.022 times 10 to the 23rd atoms. And how much does 1 mole of carbon weigh? 12.011 grams. So then 12.011 grams is equal to Avogadro's number of atoms. So 6.022 times 10 to the 23rd to 12.011 grams. You can do that on your calculator. If you compare these two equations, we've got 1.3 times 0.2, we've got Avogadro's number in the numerator, we've got 12.011 in the denominator. We can tell that we're going to end up with the same answer. It's just a slight difference in how you think about it. Either way is very valid. So we come up with the same answer. Any questions? A titanium cube contains 2.86 times 10 to the 23rd atoms. What is the edge length of the cube? The density of titanium is 4.50 grams per cubic centimeters. Now this is a sort of word problem that I enjoy and drives a good half of my students wild with frustration. So let's work this through. So you read this and you might be thinking, "Wah!" It's okay. Pull the numbers out. 2.86 times 10 to the 23rd atoms. What kind of atoms? Titanium, right? So atoms of Ti. And then we've got a density. This is 4.50 grams over cubic centimeters. When it's typed, it's written with a slash because it's so much easier than getting out the math equation editor and making a vertical fraction. I typed this, and that's exactly why I did it that way. When you write it by hand, it's just as easy to make a vertical fraction. The vertical fraction helps you to see more clearly. Gram is in the numerator, grams on top, cubic centimeters on the bottom. So write it as a vertical fraction. So we've got those two numbers. And then we wrote down the numbers. What are they asking for? Edge length of cube. Edge length. Okay, of a cube. Well, maybe drawing a picture will help us. So let's draw a cube. And here's the edge, and maybe we'll call it L for length. It's a cube. That means that all three dimensions are the same, right? So this is also L, and that's not what I wanted. And no. This one, from here to here, that's also L. Do you remember the equation for the volume of a cube? It's the edge cubed. Geometry. Okay, so what can we do here? Well, we're starting with a number of atoms. Just by looking at the units on here, we can be pretty sure that number of atoms is what we're starting with, and that the density is actually going to be used as a conversion factor. This gives us a relationship between mass and cubic centimeters. So now we can start to hammer out a path We're going to start with atoms, and we want to end up with length. What might be a convenient unit for this length? Centimeters? Because this density has the volume listed as cubic centimeters, right? And we know we could calculate the volume using this equation, right? If we knew what the length was. So somewhere in here, we're probably going to have to use that. This has the unit of gram. Could we get from atoms to grams? We just learned how to do that. Do you want to go through moles, or do you want to go straight from atoms to grams? Straight. I prefer that. Fits on the slide better. We can go from atoms to grams, knowing the molar mass of titanium from the periodic table and knowing Avogadro's number. Now, going from grams to centimeters. Well, we can't really go directly to centimeters, but what does the density allow us to go to? To the volume in cubic centimeters, right? How are we going to get from cubic centimeters to centimeters? We're going to have to use an equation. So this part is unit conversions. This step from cubic centimeters to a length is using an equation. So here we're going to use that equation, volume equals length cubed. So now we can start. 2.86 times 10 to the 23rd atoms. And we're going to have two conversion factors. We're going to have grams here with atoms on the bottom. And then we're going to have cubic centimeters with grams on the bottom. If you're still a little iffy on dimensional analysis, today in lab is when you need to figure it out. Because this last step uses an equation, I'm going to find this result and then use the equation. I'm not going to just tag it on. So relationship between cubic centimeters and grams, that's the density, 1 cubic centimeter, 4.50 grams. That was given to us. That's this guy right here. This relationship we get from the periodic table. Titanium, 47.88. Grams is equal to Avogadro's number of atoms. So we get out our calculators, 2.86 EE23 times 47.88 divided by 6.022 EE23 divided by 4.50 equals equals 5.053. Now before I wrote down a whole mess, how many significant figures does it look like our final answer is going to have? 3. This one has 3. This is 4, 4, and 3. So I'm going to write down 2 extras and call it good. So I've already got 1 extra. I'm just going to write down 1 more. And so there is my last significant figure, and this is the unit of cubic centimeters. Now that's not my final answer. I've run out of room, so I'm going to go in here just because I can. So we know that the volume is equal to 5.0532 cubic centimeters, and that is equal to that edge length that we seek cubed. So what we need to do is we need to take the cube root of both sides and find out what L is. So if I take the cube root of this and the cube root of that, So your calculator should have a button that allows you to do that. And sometimes you have to mess around with it a little to remember how it works. On mine, I have to press the, is that right, 3 first? Yeah, I think that's right. So I come up with L being equal to 1.71602, just doing 3 sig figs, and the unit would be centimeters, so 1.72 centimeters. Anybody else get that number? Yeah, okay. Is that a reasonable answer? It's a, reasonable size for a cube. That number of atoms is in the ballpark of a mole of atoms, and so we would expect that this is something that's large enough to see. Any questions? A question like this could certainly show up on an exam. Yes?
When I got 5.8 and all that, I got times 10 to the 46.
Okay, if you're getting times 10 to the 46, then we have an issue with your calculator and how you're entering scientific notation. So we can get that straightened out in lab. Any other questions? When you're multiplying and using scientific notation, usually things work out okay. It's when you divide by something in scientific notation that it really shows up that, oh, wait a minute, we need to put that in a different way.